So let's now talk about poles and zeros. We could write this transfer function also in another way. We could write it as a product of terms, and the terms are then defined by the solutions of the numerator and the denominator of this transfer function. And the solutions of the numerator are called the zeros, and solutions of the denominator are called the poles of the system or the transfer function. So here they are, the poles and the zeros. And the solution of the poles, we call them the solutions of the characteristic equation, which stems from the homogeneous differential equation. The sum of the derivatives of the output signal equals 0, even though there is no input signal, which means there is still energy stored in the system. So that is what it says, result of energy storage. There is an output signal which is non-zero, and there is no input signal at that time instant. Zeros are complex frequencies at which there is no signal transfer. Then the numerator equals 0. Poles and zeros, of course, are real or pairs of complex conjugates because they stem from the coefficients of the differential equation, and together they constitute those coefficients of the differential equation. We can write the characteristic equation of the system also as a set of first order differential equation, and then we have the so-called companion matrix of the system like this. Here you find the coefficients of the differential equation and the other parts of the companion matrix. And the property then is that the determinant of S times the identity matrix minus the companion matrix is the characteristic equation, and solutions of this are called the poles. So the eigenvalues of the companion matrix are the poles of the system. That's important. So there you recognize what we call the generalized eigenvalue problem from mathematics. Poles and zero plots, usually we plot them in a complex plane like a circle for a zero and a cross for a pole. And we can relate the both plots, the magnitude and the phase characteristic, to the pole zero plot as sketched in this diagram on the right. So the vector 2 as 0 is the length of one term in the numerator, and the vector from omega, the omega that you want, to the pole is the length of the term in the denominator. And if you multiply all these terms, you have the magnitude of the transfer function. The angles you can find in a similar way. It's the angle with the positive x-axis from the vector g omega, the frequency that you want to have, to the pole, or to the zero, of course. So here it is again, the expression that we have seen before. And here is how the arguments and the magnitude are calculated. Impulse and step response also relate to poles and zeros. We know that the impulse response is the inverse Laplace transform of the system function. And here we can calculate it from the residues. And interesting is that you see that there is the exponential function there. There will be the pole frequency as an argument if you calculate the residues, which means that all poles must have a negative real value to be stable. And the unit step response is the the integral, of the unit impulse response. That's what we need to know before we start dealing with the next stuff, which is network theory and finding poles and zeros, because we need this mathematics to understand how we are going to transform our network equations so that we can estimate poles and zeros.